You're watching a Channel 98 NBISD TV production.
Hello out there in TV land. Welcome to another great episode of Deja Vu. It's Algebra 2. As always, I'm your host, Kevin Corpy. Today is Lesson 19. You've tuned in for a good one. We talked about logs last week, and we're talking about log or logarithms again on today's show. We're going to go a little bit more in depth into some of the unique properties of logarithms, something you don't want to miss. So download the worksheets from the district website and play along with me right there at home, and let's learn a little bit about logarithms. All right, Lesson 19, Properties of Logarithms. Now, we looked at a very important theorem last time. It was a conversion theorem, what I called it. And it was a theorem that allowed us to convert between exponential functions and logarithmic functions of those two being inverses of each other. And it's so important that I've included it again at the top of today's show. Here it is. It says y equals b to the x, exponential, if and only if log base b, so it's the same base, of y is equal to x. And so remember, we want to convert from one to the other, we use this. If we convert from log to exponential, we have b to the x, which is this, equals y. So remember that the log is nothing more than the specific exponent to which we must raise a particular base to achieve a specific number. Okay, that's all a log is. A log is an exponent. Now, what are we going to choose for our choice of base for logs? Well, there's two typical usual choices that we like to work with, and it's because they show up in science and they show up in mathematics quite a bit. And consequently, our calculator is pre-programmed to handle both of those two bases. The first base is going to be base 10. Base 10 is something that you'd encounter in a science class, and it's called the common base. It is so common, we just call it the common base. So if I was to write that as log subscript 10, log base 10 of x, we don't actually have to write that. If we just write log of x, it is understood that it's going to be base 10. Okay? So just log of x without a specified base is going to be the common log, and its base will be the common base, number 10. It is, in fact, found on the calculator. And let me show you. I have my calculator right here. It's a TI-83 plus. We'll zoom in on it. If you notice right here to the left of the 7, we have an LOG button. Okay, that's log base 10. Also, notice the second command right above the log. See, if you hit the second, the yellow button, then hit the log, it's 10 to the x. Okay? And it's not just a strange coincidence that log base 10 and 10 to the x ended up on the same key. The programmers of the calculator did that because they are, in fact, inverses of each other. Okay? Not a coincidence there. So log base 10 is the common base. What other base shall we use? Well, we can also use a famous base. That's the famous irrational number known as the number e. It's the symbol, like pi is 3.14159-ish. E is 2.718-ish, okay? It's known as Euler's number. It's also known as the natural base. Sometimes it's referred to as the banker's number. But it shows up a lot in nature, and that's why we call it the natural base. So if I have a log base e, which is written like this, we have a special notation for that as well. We write it as ln of x, and we read that as the natural log of x. Even though the L is first and the N is second, we read it as the natural log of x, okay? And it is also found on the calculator. And let me show you where that is. If you notice, right close by to the LOG command, which I'll focus it right there, right below the LOG is the capital LN. That's the natural log button. Okay, so that's log base E. And once again, if you zoom in and you look at the second command on that key, it is E to the x, where e is the same natural base. So remember, logs and exponentials are inverse operations. So the log base 10 and the log base e have pairings on the calculator with their inverse operation, which is the exponential. Now, e is such a popular number in mathematics that you can actually get to the e by hitting second natural log. And if you slide over here and look at the division key, if you hit second division bar, you just have e by itself, which is e the number, not e raised to a certain power. So there's two shortcuts on basically on the face of your calculator to get to e. Pretty important number. All right, but those are the two usual choices of bases that we use when we're talking about logs. But remember that we can actually refer to log of any base. Okay? All right, so what are these basic properties of logs? Well, let's start with number one. It seems like a good place to start. Here it is. It says log any base of x plus log of the same base of y is equal to the log of the same base of the product xy. Ooh, marvel at it. What does that mean? That means the sum of two logs is equal to the product, or the log of the product, sorry. Ooh, let me say that again. The sum of the logs is equal to the log of the products. That's a very nice feature because we're basically switching operations. We're taking an operation of addition and it's becoming an operation of multiplication. Now this property works both ways. So if I started on the right-hand side, I can basically start with a product, or the log of a product, and turn it into the sum of two logs. So each of these factors, x, y, that are being multiplied together, actually get their own log, and then we add the results together. Now, if I'm starting with something on the left, which is two terms, and I'm condensing it down into something on the right, we actually call that condensing it. We're writing it in kind of in a smaller package. If I start with something on the right that's well written with only one log, I can write it like this, or I can expand it to look like that. So if I'm going that way, we call it expansion. So we can talk of condensing and expanding using this property. Now let me kind of show you this thing in action here. For example, if I have log of 10, which remember that means base 10, log base 10, the common log, plus log of 1,000. What does the property say? Well, the property says that I can write log 10 plus log of 1,000 as log of 10 times 1,000. Okay? That's what the property says, and I'm going to get an equivalent answer. Well, let's go ahead and work this out a little bit. Let's go ahead and work down the right-hand side. We know that we can actually multiply those two together. So 1,000 times 10 comes out to be 10,000. A 10 with 3 zeros behind it. Now, remember the property that we had on a previous show. Sometimes it is helpful, even though it's understood without the 10 being there, that it's base 10. Sometimes it's helpful to write the 10 back in there. So this is log base 10. We can write 10,000 as a power of 10. It happens to be 10 to the 4th. Now remember the property from another show, last show, where I said log base b of b to the x is nothing more than x, because the log and the exponential undo themselves and we end up right back where we started. So log base 10 of 10 to the 4th would equal 4. So that's what we get on the right side if we actually use the property. We get the number 4. It's worth, at least originally or initially, to go ahead and verify that we get the same answer on the left if we had not condensed it. Let's try it. Here I have log base 10 of 10, which I'm going to write like this, log base 10 of 10. If there's no exponent, it's implied to be a 1, plus log base 10, and 1,000 is the same as 10 cubed. Okay? So now I can use the same property right here. I can use it twice right there. So log base 10 of 1 is 1, plus log base 10 of 10 to the 3rd is 3. And what's 1 plus 3? It is, in fact, 4. So we get 4 equaling 4. And that's a true statement. So we verified the property. And it works basically for any value. Now let me show you something else here which is interesting. It's another reason why this works and how it's related to exponentials. If I come back up to this, let's say that I use the property and I multiplied them together. Notice that the sum turned into a product and the product turned into a sum. If I would have rewritten this right here without multiplying the numbers but write them in terms of their bases, that's the same as log of 10 to the 1st times 1,000, which is 10 to the 3rd. Okay? If I now combine what's inside the parentheses, I use my rules of exponents. And remember what the rules of exponents say. It says when you're multiplying two exponentials and their bases are exactly the same, you add the exponents. So this operation of multiplying 10 to the something times 10 to the something, because they're the same number, turns into an addition operation. I'm adding the exponent. So I get 10 to the 1 plus 3, or down here, 10 to the 4th, which is in fact 4. So the very reason why this log property works, why we can write the sum as a product and the product as a sum, has everything to do with the rule of exponents. When you're multiplying, you can just add the exponents when the bases are exactly the same. Okay? Let's look at another property right here. This property is very closely related. It says log base b of x minus log base b of y. We're subtracting now. Well, it's not going to be exactly the same, but it's very similar. It's equal to log of the same base of x divided by y. So the difference of the two logs is equal to the log of the quotient. All right? Now let me show you an example. Let's say I have log base 2 of 32 minus log base 2 of 4. The first term is my positive term. The second term is the negative term. What I want to do here is I want to actually condense this. Okay? There's two logs. I want to write it as a single log. Well, we need to make sure the logs are of the same base, and they are. They're log base 2. So to condense it by the property, I can pull log base 2 out in front. The positive term right here is going to go in the numerator, and the negative term, the y, is going to go in the denominator. So in this case, the 32 was the positive term, and the 4 was the negative term. So subtracting these two logs is the same thing as taking the log of this quotient. Well, what is 32 fourths? 32 divided by 4 is 8. Now, can we evaluate this as of right now? Well, we can't plug it into the calculator directly because it only handles base 10 and base e. But we can use that property that we use back up here. If you can write this number 8 as a power of 2, we'll have it. And we can, incidentally, we can write 8 as 2 times 2 times 2, which is 2 cubed. Okay? So now we have log base 2 of 2 to the third. That has to equal 3. And remember what that means. That means the log is 3. That means I take my base 2, I raise it to the third power to achieve my given value of 8. So this property also works. Okay? There's a couple more. Okay, this next property is perhaps my favorite, if I dare say I have a favorite log property. I like them all, really, but this one's pretty nice. Okay? Here's what it says. It says log base b of x raised to the nth power. So the process of raising something to a power, exponentiating, turns into this. It turns into n times log base b of x. In other words, we could take this exponent out in front and turn it from an exponent to essentially a multiplier, a constant multiple or a scalar multiple. So it takes the process of exponentiation and turns it into multiplication, which is exactly what we do when we look at our rules of exponents. If you remember the rule of exponents, it says x to the n raised to the nth power. We're taking something and we're raising it to a power, just like down here we have x and we're raising it to the n. Well, what's the rule of exponents say? It says we have to multiply that. So that becomes x to the n times m. So again, the process of raising something to a power turns into a multiplication. Same thing here, raising it to a power, bring it out front, becomes a multiplier. That's a nifty one. Okay? Let's look at an example. Natural log of 2 to the third, which we know to be natural log of 8. Okay? 2 to the third is in fact 8. Should be equivalent then to a different form of that. If I have 2 to the third power, 3 is the exponent. The rule says I could bring the exponent out in front and call that 3 times the natural log of 2. So essentially, 3 times the natural log of 2 should equal the natural log of 8. And if I told you that, you'd kind of have to take my word on it. But you could verify this on the calculator because your calculator can handle base e, the natural log. So if you pull up the calculator, you'd punch it in just like this, 3 ln. If you notice when you hit the ln, it does open the parentheses. So when you type in your 2, it's a good habit to get into closing it. You get 2.079. If you just typed in natural log of 8 and hit enter, you get the same exact number. So the calculator has verified that this property does work, and you can take my word for it, it works every time. Now, what happens if we're trying to evaluate a log, and it's not base 10 or it's not base e, and we want to know what the decimal approximation is? Well, you're in luck, because there's another property, which is really a formula called the change of base formula. And here's what it says. It says you have log of a particular base b. Okay, call it 7, 5, whatever. You can change it to any other convenient base, call it a. And we'd like to be using 10 or base e. Here's what you do. You take the log of your new base of x, just like before, and you divide it by the log of the new base of your old base. This is going to be a number down here. Okay? Now, because we're going to be interested in using base 10 and base e, we can make this specifically tailored for our use. So I could say it's log of x over log of b, or the natural log of x over the natural log of the old base. Okay, and we could type those directly into the calculator. Now, people get confused. Where does the x, where does the b go? If you remember that b is the base, it's kind of down here in the basement, right? On the log, it's a subscript. Well, when you're using the change of base formula, notice the log of b is in the basement of the fraction. It's down here in the denominator, okay? So remember the b, the base, goes in the basement. Now let me show you how to do this. Log base 9 of 27. If we want to know what that is, we don't have base 9 in our calculator. We only have 10 or base e. We can write it using the change of base formula. So we can write it as log of 27 divided by log of the base 9, which should be equivalent to the natural log of 27 over the natural log of 9. And those you can directly punch into your calculator. And I have the calculator screen right here. Notice natural log of 27. I have to close the parentheses now. It's important before you divide by the natural log of 9. You get 1.5, which is 3/2. If you type in the log of 27 divided by the log of 9, you get the same number. Now you got to be careful here because the ratios of the logs ends up being the exact same number. But that doesn't mean that the numbers themselves are equal. For instance, the natural log of 27 is 3 point something. The log of 27 is only 1 point something. So the numerators and the denominators are not equal to each other. It's the ratios that are equal. Like 1/2 and 4/8 are equal. They're equivalent, but the numerators aren't the same. 1 does not equal 4. Now, you actually could do this a different way. That's what's wonderful about logs. You've got a lot of different options here. You can use the change of base formula, or you can write 27 as a power of 9. And it is going to be kind of tricky because 27 is not a direct power of 9. It's a fractional power. It's actually raised to the 3/2 power. So having your calculator handy will allow you to write the log now of any base in terms of base 10 or base e. All right, let's take a real short break, watch these public service announcements, but don't go away because we're going to be right back. And while you're gone, think about this. When those birds, those migrating birds, fly overhead like duck or geese, they fly in that V formation, right? Have you ever noticed that one of the legs of the V is always longer than the other? Why is that? I'll tell you why when you get back.
I smoked weed and nobody died. I didn't get into a car accident. I didn't OD on heroin the next day. Nothing happened. We sat on Pete's couch for 11 hours. Now what's going to happen on Pete's couch? Nothing. You have a better shot at dying out there in the real world. Driving hard to the rim, ice skating with a girl. Now you want to keep yourself alive? You go over to Pete, sit on his couch till you're 86. Safest thing in the world. Me? I'll take my chances out there. Call me reckless.
The odds of a child becoming a professional golfer? 1 in 140,000. The odds of a child being diagnosed with autism? 1 in 150. You know the odds of autism. Now learn the signs. Go to autismspeaks.org.
Welcome back to Deja Vu. It's Algebra 2. I'm your host, Kevin Corpy, talking to you today again about the properties of logarithms. Okay. So why does the V formation that the migratory birds fly in, why is one leg always longer than the other? Does it have anything to do with the efficiency of flying, maybe into the wind? No. The answer is there's more geese in the longer side. Some things are obvious. Back to math. All right, so let's go ahead and start using some of these properties in combination with each other. Here we have an expression. It's the natural log of 3x squared over 2y cubed z to the 4th. Oh my goodness, that looks pretty ugly. One of the nice things about the properties of logs is working with this directly will be kind of difficult, okay? But I can turn this ugly quotient with multiple products and exponents into something that's just a string of terms, each having their own log. So here's what we're going to do. Anything that's multiplied in the numerator, remember we can expand out and we add them together. And anything that's in the denominator, we have to subtract, and they get their own logs. And then the other property said exponents can come out front. So let's do this in 2 steps. I'm going to go ahead and expand it first using the first 2. So I have the natural log of 3, that's my first factor, plus the next factor in the numerator is x squared. So it's the natural log of x squared. So that's expanding the top. In the bottom, I have 2y cubed and z to the 4th. That's 3 factors. So I will subtract, and I'm going to put parentheses here, because I'm going to use the rule that I'm multiplying in the denominator, so I have to add them. But I need the parentheses here because they all take place in the denominator. So it'll be minus the natural log of 2 plus the natural log of y cubed, and then the last one is z to the 4th. So plus the natural log of z to the 4th. So they each get their own log. Now that's step 1. The parentheses are important. Now in step 2, we'll go through and we'll use the third property. If anything has an exponent, we'll bring it out front and make it a scalar multiple, okay, a coefficient essentially. So I have the natural log of 3, that's good, plus, now the x squared has a 2. That 2 comes out front. So it becomes 2 times the natural log of x. Now I'm going to distribute the negative all the way through. That's minus the natural log of 2, plus, I have a 3 here, it'll come out front. So plus 3 times the natural log of y. And then I have a 4 on this term, and it comes out front, plus 4 times the natural log of z. And I forgot to do something here, which I catch before I leave the problem, and I have to distribute the negative, like I said. Or I can do that in a separate step. But notice what we have here. We just have a string of natural log terms, and all of them are logs of single objects, and none of them are raised to higher powers. Anything that was multiplied in the numerator has a plus sign in front. Anything that was multiplied in the denominator now has a negative sign in front, okay? And all the exponents are now coefficients. Got it? That's expanding it out. So now I can work with each of these terms and think about it as 1, 2, 3, 4, 5 smaller little problems than one big giant ugly problem, okay? And inch by inch, anything's a cinch, right? Let's look at it in reverse. We want to now condense the following log expression. So now we're going to package this thing back up, all right? I've got 2 log of 3x minus 3 log of y plus log 2 plus 2 log x minus 4 log z. Notice that there are 1, 2, 3, 4, 5 terms, and each of them are log base 10. If the last thing we did when we were expanding was bring the exponents about as coefficients, the first thing we're going to do when we're packaging it back up is bring any coefficients that are out front and put them back up as exponents, okay? So I have an exponent, or coefficient there, there, and there, and there. Those all get brought back up. So this becomes log of 3x quantity squared minus log of y quantity cubed plus log of 2 plus log of x squared minus log of z to the 4th. Okay? So, oops, I forgot my g. There we go. Now, I go through, and since they all have a log, I know I can pull a log out front. Positive terms are going to be multiplied in the numerator. Negative terms are going to be multiplied downstairs in the denominator. Since I have negative terms, I know I'm going to have a fraction, so I'm going to make a little place for it. Now let's go through and do the positive terms first. That's a positive term, so I know the quantity 3x squared is in the numerator. We're going to change from addition to multiplication now. So 2 is a positive term, so it's times 2. There's an x squared. So I had 3 positive terms, and they're all being multiplied on the top. The 2 negative terms now are right here. I got a y cubed, so that's going to be in the bottom, times a z to the 4th, which is also multiplied in the bottom. Now what you've done there is you've effectively condensed it. But now you want to get inside there and try to see if you can simplify things, expand things out, divide out common factors, and all that good stuff. So let's see what that becomes. We get the log base 10. Well, 3x quantity squared is 3x times 3x, which is 9x squared, times 2 times x squared, all over y cubed, z to the 4th. So I did one operation there. Then I'll re-examine, can I do anything else? Well, I got some numbers here I can combine. So that becomes log of 9 times 2 is 18. X squared times x squared, that's x to the 4th, over y cubed, z to the 4th. And believe it or not, that right there, since I've divided out all the common factors, collected all my like terms, is the condensed version. That's the smallest package that we can put all this back into, condensing, using the properties of logs. They might seem overwhelming at first, but there's only 3 of them. If you practice them individually, then you can start stringing them together and looking at more and more complex expressions. And practice, because it is a little bit of fun, I have to admit. Now it's time for
Deja Review.
Okay, we're going to look at an application today of logarithms. And many things in the real world are measured in log scales. Sound is measured in terms of logs. Light intensity is measured in logs. pH levels are measured in logs. And earthquakes are measured in logs, namely the Richter scale. So seismologists, the people who study earthquakes, they actually use the Richter scale to express the energy or the magnitude that an earthquake gives off during an earthquake. The magnitude we call m, and the energy that it releases is typically measured in ergs, which we're going to call capital E. Now here's the equation for the earthquake. Notice that it's the magnitude is equal to 2/3 of the log base 10. Science uses base 10 quite a bit. of the energy released over 10 to the 11.8. Now this 10 to the 11.8 is kind of like a constant that establishes a basis by which all the other earthquakes can be compared. Okay, now because it's a log scale base 10, what that means is if something is a level 1, an earthquake, versus a level 3 earthquake, that difference is 2. 3 minus 1 is 2. That doesn't mean that the level 3 is twice as strong as a level 1, nor is it 3 times as strong. But because the difference is 2, and it's a power of 10, it's 10 squared, or 100 times stronger. So level 3 is 100 times stronger than level 1, because it's exponents, base 10. Now, this is an example that most of us are probably, we remember, the tsunami that devastated parts of Asia in December of 2004. It was spawned or begun by an earthquake that started out in the ocean that registered a magnitude of 9.3. Huge earthquake. Okay? What we want to know is how many times stronger or how much more energy did that earthquake release than the one that struck San Francisco in 1989, which I remember it interrupted the World Series between the Giants and the Oakland A's. It only registered 6.9. So how many more times strong or how much more energy did the 9.3 earthquake register than the 6.9? Here's the calculations. What we're going to do is we need to find the energy released by both of them. And we're kind of running out of time, so I'll walk you through it. And if you want to get the calculations, just email me and let me know. But I know the magnitude. So if I look at the Asian earthquake, I can plug it into this formula. It measured what was it, a 9.3 on the Richter scale. So that's the magnitude. So 9.3 is equal to 2/3 log of E over 10 to the 11.8. So I've plugged in this number. Now this isn't one formula with only one unknown. I need to solve for E. So how can we solve for E? Well, I need to isolate the log. So I will multiply both sides by 3/2 or 1.5, which will get rid of that. And that will give me 13.95 equals log of E to the 10 to the 11.8. Now we have to convert from log to exponential. This is base 10. So remember the conversion formula? It says 10 raised to this power. So I get 10 to the 13.95 power equals this, the argument right here, which is 10 to the 11.8. And now I'm almost there. Now I solve for E by multiplying both sides by the denominator, and we get 10 to the 13.95 times 10 to the 11.8, which when I add those together, I get E, the energy in ergs was 10 to the 25.75 power ergs. Okay? If we do the same thing for the San Francisco earthquake, we'll see that it only registered 10 to the 22.15 ergs, the San Francisco. Okay? So if I divide these out, it's essentially subtracting their exponent. You get 3981, which actually ends up being the difference, 10 to the 3.6 power. So this number right here is what we're looking at. That means that the Asian earthquake that caused so much devastation with the tsunami was more than almost 4,000 times stronger than the earthquake that shook San Francisco in '89, which was pretty devastating in itself. That gives you an idea of logs, and it also gives you an idea of how strong and devastating Mother Nature can be. Well, all good things must come to the end, and this episode is about over. We've run out of time. So remember that logarithms, although initially they can kind of make you tremble like a giant earthquake, with enough practice, you can become less fearful of them. In fact, you can master them, and dare I say, you can even have fun with them, like I do. Anyway, until next time, I'm Kevin Corpy, reminding you to do your homework.